Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. GATE 2022 Chemical Engineering. Previous year questions and detailed solutions. Mass Transfer Part 1. In this video course, we will discuss Chemical Engineering question number 5, question number 13, question number 15 and question number 25. Please subscribe to the channel. It will motivate us to produce more valuable knowledge content for your career progress. So subscribe now before you forget. GATE 2019 Chemical Engineering paper had 8 questions in mass transfer. We will cover 4 of them in this video with detailed analysis. Question number 5. For a binary non-ideal AB mixer exhibiting minimum boiling azeotrope, the activity coefficient gamma I, where I is equal to A, B, must satisfy option A, gamma A greater than 1, gamma B greater than 1. Option B, gamma A less than 1, gamma B greater than 1. Option C, gamma A equal to 1, gamma B equal to 1. Option D, gamma A less than 1, gamma B less than 1. Question analysis and solution. For a non-ideal binary mixture of components A and B, we can write PA is equal to YA into capital P, which is equal to XA, gamma A, PSA. For component B, we can write PB equal to YB into capital P, which is equal to XB into gamma B into PSB. Where PSA is the vapor pressure of component A, PSB is the vapor pressure of component B, XA is a mole fraction of component A in the liquid phase, XB is the mole fraction of the component B in the liquid phase, P is the total pressure. YA is a mole fraction of component A in the vapor phase. YB is a mole fraction of component B in the vapor phase. PA is a partial pressure of component A in vapor phase. PB is the partial pressure of component A in vapor phase. Gamma A is the activity coefficient of component A. Gamma B is the activity coefficient of component B. So the total pressure P can be written as P equals PA plus BB. So P is equal to XA into gamma A PSA plus XB into gamma B PSB. For the minimum boiling azeotrope, the conditions to be satisfied are gamma A and gamma B must be greater than 1. The reason being, for non-ideal solutions exhibiting minimum boiling azeotrope, the vapor pressure of pure component is higher than that is predicted by the Raoult's law. So in the expression PB equal to YB into P equal to XB into gamma B into PSB, the gamma b is greater than 1. The same is true for component A. The solution exhibits positive deviation from Raoult's law. Hence, activity coefficient gamma is greater than 1 for both the components. Likewise, non-ideal solutions exhibiting maximum boiling azeotrope have negative deviation from Raoult's law. Hence, the condition to be satisfied are gamma A and gamma B both must be less than 1. This is a concept with regard to the non-ideal solutions. Hence, the answer to the question is option A. Question number 13. The correct expression for the Colburn J factor for mass transfer that relates Sherwood number, Reynolds number and Schmidt number is option A, Sherwood number divided by Reynolds number multiplied by Schmidt number to the power 1 by 3. Option B, Schmidt number divided by Reynolds number to the power 1 by 2 multiplied by Schmidt number. Option C, Sherwood number divided by Reynolds number to the power 1 by 2 multiplied by Schmidt number to the power 1 by 3. Option D, Sherwood number divided by Reynolds number multiplied by Schmidt number. Question analysis and solution. The Colburn factor for mass transfer is expressed by JD equals Kc in Schmidt number to the power 2 by 3 divided by U. This analogy is valid for gases and liquid within a range of Schmidt number from 0.6 to 2500. The key to find the solution for this problem is that you should find out which of the given expression options satisfies the equation for J factor. The expression option A satisfies J factor. We will see how it is arrived at. The dimensionless number Sherwood number is expressed as the ratio of molecular mass transport resistance to the convective mass transport resistance, which equals Kc into D divided by DAB. The dimensionless number Schmidt number is expressed as the ratio of momentum diffusivity to mass diffusivity, which equals mu divided by rho into DAB. Similarly, the dimensional number Reynolds number is expressed as the ratio of inertial force to the viscous force, Re equals to du rho by mu. Now substitute each of these dimensionless numbers in the four options given one by one and check which option satisfies the expression for J factor given above. First, option A, which is Sherwood number divided by Reynolds number into Schmidt number to the power 1 by 3. Substituting and simplifying, you get Sherwood number divided by Reynolds number into Schmidt number to the power 1 by 3 simplifies to Kc into schemic number to the 2 by 3 divided by U. This satisfies the expression for JD. Other options do not satisfy the expression for JD. Thus the answer for question is A. Before I move to the next question, I would like to remind you that the questions related to dimensionless numbers have been asked repeatedly in the GATE exam in the previous years. So make notes of them for ready reference and memorize them. Question number 15. 3 distillation schemes for separation of equimolar constant relative volatility ABC mixture into nearly pure components are shown. The usual simplifying assumptions such as constant molar overflow, negligible heat loss, ideal trace are valid. All the schemes are designed for minimum total reboiler duty. The 3 schemes for separation of ABC mixer is shown here. Given that the relative volatilities are in the ratio alpha A is to alpha B is to alpha C equals 8 is to 2 is to 1, the correct option that arranges the optimally designed schemes in the ascending order of reboiler duty are option A 1, 2, 3, option B 3, 1, 2, option C 2, 1, 3, and option D 3, 2, 1. Question analysis and solution. Analyze the problem data first to get an insight into the approach for the solution. The 2 important data given are 1. The feed mixture of A, B, C are equimolar. 2. The relative volatility ratio alpha A is to alpha B is to alpha C equals 8 is to 2 is to 1. What do you infer from the relative volatility data? A is the most volatile and C is the least volatile. Component B lies in between. What do you infer from the feed composition? The feed is equimolar, meaning the components A, B and C have the same concentration in the feed. These 2 data are very important in determining the distillation sequence in multi-component separation. For separation of a mixture of given components, that is, the relative volatility alpha is fixed. The difference in annualized cost between different scheme is a function of the vapor flow rate passing through the columns. Vapor flow is a reasonably good measure of cost because it is a major factor in determining reboiler and condenser duties as well as column diameter and reboiler and condenser areas. Remember, it is a reboiler that generates a vapor from the liquid flowing to the bottom of the column. Hence, the energy consumed or the reboiler duty is proportional to the molar vapor flow rate of the column. The key to crack the question lies in finding out which scheme will generate the least amount of vapor flow through the columns. Reboiler is an integral part of the distillation system, and understanding of how the reboiler works is essential to every chemical engineer who aspires to work in a refinery or petrochemical plants. SPEC e-learn channel has published 2 videos on reboiler. I would recommend you to watch them. Coming to the problem, the design requirement for column sequencing is the optimum reboiler duty for separating A, B and C into pure components. 3 sequence schemes are given to select. Let us analyze the 3 schemes one by one to understand what is happening. Scheme 1 separates the most volatile component A with relative volatility 8 as top product from column 1. The B and C components are removed from column 1 bottom and sent to column 2 for separating into pure B and pure C. The scheme 1 separates the most volatile component A with alpha A equal to 8 as top product from column 1. The B and C are removed from column 1 bottom and sent to column 2 for separating into B and C. In the column 2, the relative volatility of component B, alpha B is equal to 2. Hence B is separated at the top and C is drawn from the bottom. This sequence of separating lightest or more volatile component first as top product and subsequent separation of B and C in column 2 is called direct sequence. The reboiler duty of column 1 is QC1 and the reboiler duty of column 2 is QC2. The total reboiler duty of the scheme 1 is QC1 plus QC2. The scheme 2 separates the least volatile component C as bottom product from column 1 as pure component. The components A and B are removed from column 1 top, each 0.33 mole, as both are more volatile and sent to column 2 for separating into A and B. In the column 2, A being more volatile leaves the column 2 as overhead product and B is withdrawn as bottom product as pure components. This scheme is called indirect scheme. In the scheme 3, the feed molar flow is split between top and bottom of column 1. All of A and roughly 32% of B is separated as distillate in column 1. The remaining 48% of B and all of C is removed as bottom product from column 1. A is separated as overhead from column 2. Component B is separated partly from column 2 as bottom product and partly as overhead from column 3. Component C is completely removed as pure product from column 3 bottom. Since there are 3 columns, the scheme 3 operates with the 3 reboilers. Accordingly, the total reboiler duty is QC1 plus QC2 plus QC3. For the 3 schemes, we can determine the vapor flow rate through the columns. As discussed earlier, this molar vapor flow rate through each of the columns is a measure of reboiler duty of the corresponding column. Thus, the total vapor for the 3 scheme is a measure of total reboiler duty for each of the schemes. The column-wise vapor flow rate for each of the 3 schemes is presented in this table. Note, this is part of the multi-component distillation column design. Hence, you must have the knowledge of the distillation column design. Since this is a 1-mark question, I don't intend to give you the design procedure. A final summary of the design calculation is given in this table for your understanding. The scheme 1 has 2 columns and the scheme 2 also has 2 columns and the scheme 3 has 3 columns. Assuming saturated liquid feed for each of the column, we determine the minimum reflux ratio, the design reflux ratio, and the vapor flow rate through the column. Finally, we determine the total vapor flow rate for the scheme. The scheme which has the minimum total vapor flow rate is the optimal design. As you can observe, the scheme 3 is the optimal design in terms of the reboiler duty. Summarizing our discussion, we can reasonably conclude that among the 3 given schemes, the reboiler heat duty Q3 will be less than that of Q1, that will be less than that of Q2. So the answer is B. Before I conclude the discussion on this analysis of this problem, I would like to state that this is a problem of distillation column design. Ideally, this question should be classified under the subject Plant Design and Economics. I chose to include it in mass transfer under distillation since this is more of a technical question. Tower sequencing is the first step in the design of distillation column for multi-component distillation. Remember the column sequence guidelines for design. Easiest separation first. When the relative volatility and feed concentration is constant, remove the components one by one as overhead products. This is direct sequence method. When the components vary widely in relative volatility, sequence split in order of decreasing volatility that removes the lightest components alone one by one in columns overheads. In other words, favor the direct sequence. When the concentration varies widely, but relative volatilities do not, remove the components in the order of decreasing concentration in the feed. When concentration of the components are almost equal, as in the present problem, even with wide variation in relative volatility, favor splits in which the molar flow between top and bottom products in individual columns is nearly as equal as possible. Question number 25. Consider a sealed rigid bottle containing CO2 and water at 10 bar and ambient temperature. Assume that the gas phase in the bottle is pure CO2 and follows ideal gas law. The liquid phase in the bottle contains CO2 dissolved in water and is in ideal solution. The Henry's law constant at the system pressure and temperature has CO2 equals 1000 bar. The equilibrium mole fraction of CO2 dissolved in water is question analysis and solution. This is a straightforward question of application of Henry's law for dilute solution. For dilute solution, the Henry's law is written as P star equals H times X. Where P star is the partial pressure of solute in the gas phase at equilibrium, H is the Henry's law constant, X is the mole fraction of the solute or gas dissolved in the liquid at equilibrium. Given that the gas is pure CO2 and the total pressure is 10 bar, the mole fraction of solute in the gas phase Y is equal to 1 and the partial pressure of solute in the gas phase is P star equals 10 times 1 equal to 10 bar. Given that the Henry's law constant H is 1000 bar, the mole fraction of solute or gas dissolved in the liquid at equilibrium by applying Henry's law is H is equal to 10 by 1000 equals 0.01. So the answer for this NAT type question is 0.01. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.